Hi, welcome to this lecture on simple cryptography. In today's lecture, we're going to look at some simple cryptographic ideas that you can do by hand in order to kind of get the basic ideas of doing encryption. And at the same time, we're going to look at some terminology that we use when we talk about cryptography. So hopefully all this will give you a foundation as we jump later into more modern cryptographic techniques. So as kind of an introduction, the word cryptography is Greek, and when you break it down, you have crypto, which means secret, and graphy, which means writing. So the word cryptography is Greek for secret writing. The basic goal in cryptography is to send messages, but no one but the expected recipient can read. But we can do a lot more with the cryptographic primitives that we come up with, but that's kind of our simple goal at this point. Send messages that no one but the expected recipient can read. So let's look at some terminology that we use. The word cryptography is a method to send secret messages using a code. The word cryptanalysis is where we try to break the code and read those messages. So these two words are kind of paired together. Cryptography is where we're creating and deciphering the messages legitimately. Cryptanalysis is where we're trying to break the code in order to read those messages. Some more terminology. Plain text. Plain text is a message in its original form before it's been encrypted in any way. Ciphertext is a message in its coded form after we've encrypted it. Encryption is the process of transforming plain text into ciphertext. Decryption is the process of transforming ciphertext into plain text. And an encryption algorithm or a cipher is the method used for encryption. So as we talk about cryptographic techniques, we're going to do some simple ones today, but more complex ones later. How do we know if a cryptographic technique is secure? Like, how do we know if it's good and that a cryptanalysis, someone who's trying to break it, isn't going to be able to? Well, we don't actually have good, hard, and fast, provable ways to verify that cryptography is good. Instead, we just get lots of really smart people to try and break it. So we have lots of really smart people who perform cryptanalysis on a given cryptographic technique. And if none of them can break it, after a long time, we begin to assume it's secure. And the longer an algorithm has gone without someone analyzing it and demonstrating a break for it, the more secure we tend to think it is. Now, as I say this, you should pause for a moment and say, well, that seems kind of, strange. I mean, what if we're wrong? Well, we might be wrong. And this is usually what happens. So someone comes up with a good cryptographic technique. We use it for a long time and no one knows how to break it. So we assume that it's good. And then eventually progress in mathematics or in other things begins to show that there might be some weaknesses in the design of that cryptographic technique. And so after that, we begin to move away from it and into something else. But today, let's talk about some simple ciphers. And originally, cryptography was performed by hand. Of course, today we do it all with computers because it requires some pretty high-powered mathematics. But originally, people did it by hand. And the goal was just to simply protect messages that were sent by couriers or individuals, because you didn't really want the courier to be able to read the message, and you didn't want people who might intercept the courier to be able to read the message. So it might have just been handwritten messages, but the goal was to make sure that no one who was transmitting them or saw them could read them except the expected recipient. And war was obviously a popular time to use something like this. Generals might need to send messages between army camps, and you don't necessarily want the courier or an enemy army who intercepts the courier to be able to read the message. One of the earliest documented ciphers was used by Caesar, and for that reason we call it the Caesar cipher. And his cipher was pretty simple. Each letter in a message was substituted by another letter that was 3 letters away. So for example, if I write out my message, then I might go through and every A in the message would become a D because I'm just substituting 3 letters away. Every P might become an S, etc., etc. So it's a simple concept. But at the time he was using it, surprisingly, people weren't able to decipher it very easily. Let's do an example just to make sure we understand it. Okay, so up at the top here, you'll see I've written the English alphabet, and I've just numbered all the letters, 0 to 25. And I'm just doing that so that we can do some math if we want to. But I've just written the letters, numbered them 0 to 25. And let's say that we have a message, attack at dawn, that we want to encrypt with a Caesar cipher. Well, we're going to shift every letter by 3. So we're going to start. We're going to take the letter A in the message. We're going to go up here and we're going to say A. So if I go 3 letters, 1, 2, 3, then that becomes a D. Okay, fair enough. I'll jump over here to T. Now with the letter T, I'm going to go again 3 letters, 1, 2, 3, and find W. All right. Next letter in the message is also a T, and it's going to have the same ciphertext letter, so I'm going to also make that a W. Again, we have A as the plain text. We've already done that one, so we'll get back D again. Now we have a new one, C. So C, if we go ahead 3, 1, 2, 3, becomes F. And K, if we go ahead 3, 1, 2, 3, becomes N. And if we continue that through the message, we can continue to encode it. Now, if we wanted to decode the message, so if you were just given this line of ciphertext here, and you weren't actually given the plain text, well, then you would just go through each letter and subtract 3. So we would start with D, we go backwards 3, 1, 2, 3, and get A. W would go backwards 3 to become T, etc., etc. So encryption is you're adding 3 to each letter. Decryption is you're subtracting 3 from each letter. So I kind of did it up here just by drawing little marks and adding and counting 3 over. But if you wanted to do it a little bit more mathematically, you could just translate the letter into a number, add 3. So if I want to do K, K is 10, add 3 to get 13, and that gets me N. But you get the same purpose. You get the same end result. Okay, so another type of simple cipher is called a shift cipher, which is really not that much different than a Caesar cipher. In fact, it's a generic version of the Caesar cipher. And in this case, we'll say each letter is shifted by N. And so in the Caesar cipher, N was 3, but we could shift by any number. So we'll do that instead. So we'll do another example. Again, we bring up our chart. So let's do N equals 10 for the same message. Okay, so if I have attack at dawn, well, I'm going to start with the letter A. I'm going to add 10 to it. I'm going to do it numerically this time. So 0 plus 10 is 10. That gets me K. Okay, so T. Okay, T is 19. That plus 10 is 29. Oh, well, my chart doesn't go all the way to 29. So maybe I'll just wrap around. So I would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 becomes D. And the other T also becomes D. That A also becomes a K. We've already done that one. And C, I'll add on 10. So I start here and I go, okay, 2. 2 plus 10 is 12. That would be an M. K, 10 plus 10 is 20. That would be a U. And I can continue that for the rest of the message. So my shift cipher here, when I do N equals 10, I can just shift it that way. And decryption would be similar to the Caesar cipher. I would subtract 10, just as you would expect. Okay, so with a shift cipher, how do you break this? If you're going to perform cryptanalysis on something like this, if someone just gave you a ciphertext that was shifted with a shift cipher and said, figure out the plain text, could you do it? Sure, why not? Let's take the brute force approach. Brute force meaning the most inefficient but still workable way we can think of. And the brute force approach here is to try every possible value for N, that magic shifting key. Well, there's actually only 26 possible values for N, because if you move beyond 26, you're just wrapping around and it doesn't matter. So there's only 26 possible keys. So could you sit down and in 10 or 15 minutes try all 26 possibilities for decrypting a message? Sure, you could. That really wouldn't be that big of a deal. So that's very feasible that you could do by hand. And it's trivial with a computer. I mean, you could write a computer program to do that, and it would be disturbingly simple and easy to handle. So a shift cipher is really not that strong of a cipher. It's really simple to encrypt and decrypt with, but the number of possible values for N is so small that someone could try all of them in order to figure out what you used, and it would be really easy for them to cryptanalyze that. So it's easy to do, but it's not very strong. Well, could we make it stronger? Sure. So let's try a different type of cipher called a substitution cipher. Now, in a substitution cipher, you generate a random set of substitutions for each letter. So here's a sample chart up here. As you can see, I've written the alphabet
on the first row, and then below it I've written all the letters but in a different order. So in this case I'm setting up a substitution cipher, meaning for every A in my plain text, on my cipher text I get a Q. For every B in my plain text I get an R, etc., etc. And all 26 letters of the alphabet are on the top row, and all 26 are on the bottom row. There's no repetition. So I always need a one-to-one correspondence. A always becomes Q when I encrypt, and Q always becomes A when I decrypt, in my example here. So let's do an example with this. So if my message is attack at dawn, and this is my random decision on the substitutions, well then performing the encryption is actually pretty simple. So the A, I go, okay, well A becomes Q. T becomes Y. A becomes Q. C becomes A. K becomes V. And I can continue that for the rest of the message. And decryption would be just as simple, except I would go in reverse. Instead of looking up in the top and reading the bottom, I would look up in the bottom and read at the top. So, Q becomes A. Y, got to search for Y. Here it is. Y becomes T. A becomes C, etc., etc. So decryption is fairly simple as well, as long as you have this table that translates the possible substitutions. Okay, so how could I cryptanalyze a substitution cipher? Well, in the brute force possibility, I would try all possible substitution combinations, right? And that basically boils down to how many different ways can I order the 26-letter alphabet. And there's 26 factorial ways to do that. 26 times 25 times 24 times 23, et cetera, et cetera, et cetera. Okay, so there's 26 factorial possible ways that I could build a substitution table. How many is that? I don't really think well in factorials. So I ran to Google, which has a nice big number calculator, and typed in 26 factorial. And what we find is that is 4 times 10 to the 26. That's a really big number. Are you going to be able to do that by hand? No. I'm not going to manually try every possible substitution table. That's absurd. That's way too many numbers. In fact, even doing that with a computer, while doable to try them all, is also not going to be very efficient. So that's really not that helpful for us. So at first glance, a substitution cipher seems pretty strong because there's a lot of possible substitution tables, and the chances of someone going through all of them by hand is really low. And doing it with a computer is possible, but still not all that exciting. Okay, so how do we cryptanalyze this? Well, let's look at our ciphertext again. I've taken away the plain text just so you can just look at the ciphertext. And I want to make a key observation. In a substitution cipher, the basic language features are preserved. So as an example, you can tell how often a letter occurs in the message. So as we look up at this message, we can see that, oh, well, Q happens a lot, and Y happens quite a bit. And this letter Y is duplicated, and it's one right after another. So the features of the language are preserved. You can tell that this letter, whatever it would be in the plain text, is repeated a lot. You can tell that this has the same letter twice consecutively, et cetera, et cetera. So, in fact, I can tell that this two-letter word, it has the same two letters that this word starts with. There's just a lot of things I can tell just by looking at the ciphertext. So even though it's not trivial for me to come up with a substitution table that was used to encrypt this, staring at it, there are still things I can tell about it, about the original message. So in order to break a substitution cipher, we typically use a technique called frequency analysis, and as well as the language features I just described. So what's frequency analysis? Well, it's a cryptanalysis technique described in the 9th century by Al-Kindi in Iraq. He was an Arab philosopher. And his observation was that not all letters in a language occur with the same frequency. And in addition to that, we also make use of the language features that I just described. And so as an example, in English, E is the most common letter. If you analyze large chunks of English text, E is the most common letter. Vowels are about 40% of all letters. And in English, vowels tend to be separated by consonants, so there tends to be a pattern with that. And we have other interesting features too, like the letter Q tends to be followed by U, et cetera, et cetera. So there's a lot of different things that we could see here. So actually, performing frequency analysis and language features on substitution ciphers is a newspaper puzzle. So back when I was in university, I used to watch students in big lecture halls in front of me who would be solving this newspaper puzzle in class instead of paying attention to lecture. But if you look at it, you can see that basically the designer of the puzzle just built a substitution table and picked a message and encoded it, and they just put it in the newspaper, and you're supposed to decipher it. But you use the language features to do that. And people who are good at this can solve something like this in 5 or 10 minutes, without really spending too much serious mental thought on it. Even though at first glance the substitution cipher had so many possible substitution tables that it seemed unrealistic to break it by hand, by analyzing it a little bit more, it becomes simple to the point that it's a puzzle that you put in the newspaper. So that causes us a problem, because that means that a substitution cipher is also not really very good cryptography. So we need to find a way to do something even stronger. So another cipher I'll call it a strengthened version of a substitution cipher. It's called a Vigenère cipher. And it's a type of polyalphabetic cipher. And polyalphabetic means that one plain text letter can become different ciphertext letters depending on where it is in the message. And in order to do this, we use a text-based key and some modulo arithmetic to perform the encryption. Frequency analysis is possible on a Vigenère cipher, but it's much, much more difficult. And it's a lot harder. You're not going to do this in a newspaper puzzle. So let's do an example. So I have the same chart that I've been putting up before, but this time I've modified it just a little bit. I've kind of doubled it, just because we're going to do modulo arithmetic with some wraparound. So I have the letters A to Z written in numbered 0 to 25, and then I have them written again in numbered 26 to 51. That way, if we're adding up two numbers and it wraps around, it's still easy to figure out which letter it is. It's just there to simplify doing the math on a slide. So for a Vigenère cipher, you need a text key. In this case, I'm going to pick the key monkey. I like monkeys, so I'll use that as my key. We're going to take our message, attack it on, and we're going to write our key underneath it, and we're going to duplicate the key every time we run out of letters. So I'll just write monkey, monkey, and just keep repeating the key underneath your original message. And then all you have to do is add up the letters. So A plus M, A is 0, M is 12. So that gets me M as my ciphertext letter. T plus O, T is 19, O is 14, so 19 plus 14 is 33. That gets me H as my ciphertext letter. T plus N, T is 19, N is 13. That gets me 32, so G is my ciphertext letter right here. A plus K, so A is 0, K is 10. That gets me K as my ciphertext letter. C plus E, 2 plus 4 is 6. That gets me G as my ciphertext letter. K plus Y, 10 plus 24 gets me 34, which is I for my ciphertext letter, et cetera, et cetera. So I could continue that process. But I'm just adding my plain text message with my key as I go through. And this removes a lot of frequency analysis techniques and even language features. Because as you look at this, okay, in the original plain text, the letter T was duplicated. But in my final ciphertext, the letters aren't the same. In addition, in this ciphertext, we see that G is used here and here. But in my original message, those are two different letters. So we don't have the same language features or even frequency analysis that you can perform. Now, the one flaw in the Vigenère cipher is that when the key repeats, well, that letter will always be, then you could perform frequency analysis on repeated points. So, for example, when my key starts, I have A plus M gets me M. When my key repeats, if my plain text letter is A plus M equals M. So in this case, this and this are the same. And they could be analyzed that way. That's actually the way that a Vigenère cipher is analyzed, is you analyze the ciphertext in order to try and determine what the length of the key is, and then you perform frequency analysis of letters at the same spot in the key all the way through. But it's a significantly more difficult thing to do. So a Vigenère cipher is much better than a substitution cipher for cryptography. Now, would we really want to use this for secret messages today? No, because you could run a computer program to handle that cryptanalysis without any trouble. But the concept of a Vigenère cipher leads us to a type of cryptography that you could use today, and that is provably good. In fact, this is the only provably secret form of cryptography. Its security is not based on the fact that other people don't know how to break it. We can provably show that it's unbreakable. And that's called a one-time pad. And a one-time pad is a Vigenère cipher with a randomly chosen key that's just as long as the message. The key needs to be shared between the two parties, the two people in the communication, beforehand. And that's kind of the problem with the one-time pad. That's actually a fairly difficult thing to do. And the key can never be reused. And like I mentioned before, a one-time pad is totally unbreakable without the key. This is the only perfect cryptography. Okay, so let's do an example. Here's my charts again. My random key is just this. It's just random. It was randomly chosen. And if that random key is shared between the sender and the recipient, then I could do attack at dawn. I could write my random key underneath it, and it's just as long as the message. It never repeats. And that's the important thing here. It's totally random, and it never repeats. Because it doesn't get repeated along the message, and it's just as long as the key, there's no way to perform frequency analysis because there's no repetition in the key, and that's what makes this unbreakable. And so if I were to do the actual encryption, going through and adding it all up, I would have a ciphertext, but there's no way to know what the original text was. And the reason for that is, like I said, the key is totally random and just as long as the message. Now, the difficulty here is that creating random keys that are shared between two parties that are just as long as the message is very difficult to do in a lot of scenarios. So I want to make a quick note here about all the ciphers we just looked at. And all these previous techniques have two basic components, and I hope you saw them as we went through. The first is an algorithm, which is something that you do to the message. So in the case of a shift cipher, my algorithm is, I take the letter and I add a number to it, and then I turn it into to that letter. The other component all these techniques have is a key. The key is a secret that I need in order to encrypt or decrypt properly. So in the case of a shift cipher, the key was the number that I shifted by. In the case of a substitution cipher, my algorithm was to substitute letters, and my key was the substitution table that I used. In a Vigenère cipher, my key was the secret word that I used, and my algorithm was to repeat the key underneath my message and just add the message and the key together. So when using these algorithms, the key is a secret. Obviously, if an attacker, someone who was trying to read your message, knew the key, then they could read it without any trouble. But my algorithm isn't a secret. The way a substitution cipher works is not a secret, but the key I use to encrypt a message with it is my secret. So I just wanted to emphasize that point. All right, so let's summarize what we've talked about. Cryptography is a type of mathematics dedicated to secret codes. We trust a cryptographic algorithm if lots of smart people can't break it. And while that may sound a little bit, shaky, in practice it seems to work pretty well. But it is an important concept to understand, is that other than the one-time pad we talked about today, no cryptographic algorithm is 100% secure. The security is only based on the fact that we don't know how to break it. We looked at 4 types of simple ciphers: a shift cipher, a substitution cipher, a Vigenère cipher, and a one-time pad. And each of these ciphers have an algorithm that's not a secret and a key that is a secret.